Hello, everyone. My name is Kirsten Hoynicke, and I'm a geophysicist at Pacific Northwest National Laboratory in the United States. I work with a team of individuals here to observe seismicity from underground chemical explosions using distributed acoustic sensing systems, and I'll be discussing the results of our work today. Traditional ground motion measurements face challenges in accurately representing seismicity near underground explosions due to signal distortions caused by factors that are independent of the source, which can locally decouple motion amplitudes from both source magnitude and type. Distributed acoustic sensing, or DAS, an optical technique that provides numerous densely spaced and highly correlated measurements, offers a promising method for characterizing the complex seismicity in such scenarios. However, this is a relatively new technology for measuring explosive ground motion, and we are working to understand the explosive signals that we are measuring before we can relate them to the underlying seismicity and event source parameters. We conducted a comparative analysis of ground motion measurements obtained using DAS from 3 overburied and tamped chemical explosion series in the western United States. These events span 4 orders of magnitude in explosive yield, with observations collected at comparable scaled ranges. However, the data acquisition methods differed significantly across the experiments. Measurements from PE1A were recorded using a horizontal DAS fiber directly buried on the floor of a tunnel, while the DAG or BCD Blue Canyon Dome series utilized DAS fibers grouted within vertical monitoring boreholes. To enable meaningful comparison of the results, we calculated peak scaled accelerations from the DAS data as a function of scaled range for each event. We identified the maximum strain rate at each location along the fiber and then multiplied that value by the phase or the group velocity derived from the data to compute a peak acceleration, and then applied additional corrections and scaling adjustments. Specifically for the horizontal data, we accounted for potential amplification due to the free surface of the tunnel floor by multiplying by another factor of 2. And for the vertical data, adjustments were made to account for incidence angle dependence given the helical configuration of the downhole fiber. The computed peak acceleration was multiplied by a factor of 2 to approximate the nuclear equivalent value and then scaled by dividing it by the cube root of the yield. The DAS results for PE1A reveal a single trend in the reduction of scaled acceleration with distance, but with an order of magnitude variability in the measured values for the single source type. This scatter may stem from a combination of factors, such as localized variations in instrument response and side effects, which will be further explored in future work by analyzing complete waveforms rather than simply peak values. Peak acceleration values recorded by co-located accelerometers show similar trends and comparable values to those observed with DAS, but with significantly less scatter. Furthermore, the DAS data help frame the amplitude reduction at the furthest accelerometer station as it looks low, but it falls within the variability observed in DAS measurements. The observed variability in local amplitude values, spanning an order of magnitude, suggests that making definitive source parameter estimates or distinguishing source types based solely on ground motion may be challenging at this distance from the source, which represents a transitional regime between hydrodynamic and elastic wave propagation regions. The observed single trend and order of magnitude variability in scaled acceleration values appears to be independent of yield, as similar patterns were observed across the medium and the small scale data sets. The downhole DAS data at small slant ranges in plots B and C exhibit artifacts stemming from the measurements at the depth of the explosion, where the waves arrive broadside, and the incidence corrections produce an asymptotic trend toward infinity. Efforts to develop a revised correction procedure to address these artifacts are underway and will be incorporated into future work. While the discrete sensors in PE1A showed strong agreement with DAS measurements, there was a notable lack of consistency between co-located downhole accelerometer values in DAG, shown in plot B, and downhole geophone values in Blue Canyon Dome, shown in plot C. The cause of these discrepancies are not well understood and remain an active area of investigation within the broader DAS research community. This may be related to a range of factors, including differences in sensor performance downhole or fundamental variations in the way DAS and discrete sensors are measuring ground motion. By comparing these results, we can gain deeper insight into the significance of the observed order of magnitude variability. When examining only the data from the discrete sensors, as shown in plot A, the values across all experiments appear to follow a single unified trend. However, this perspective changes when considering only the DAS measurements in plot B, where each experimental series exhibits a distinct trend despite the variabilities in the values of an individual trend. Note the small-scale BCD data plot intermediate between the large-scale PE1A and medium-scale DAG data. When the single-point sensor data is combined with the DAS measurements in plot C, the overlap of the discrete values with the PE1A DAS data obscures differentiation between the experimental series, making it challenging to establish clear distinctions. Another approach to evaluate the performance of this technology is by comparing it with the empirical models derived from observations of chemical and nuclear explosions. However, empirical models are not available for the transitional region under consideration, and existing models are unlikely to account for the fine-scale geologic features that may influence results in this area. To explore potential comparisons, we begin by linearly extrapolating empirical models designed for strong motion conditions into this transitional region, as shown in the plot A. The models, which are based on comparable emplacement geologies, were derived from the works of Parrott, Bass, and Ford. The extrapolated Rainer Mesa Tuff model, the orange line in plot B, closely aligns with the PE1A DAS and accelerometer data, fully capturing the observed trend and encompassing the variability within a confidence interval of 1 standard deviation, shown with the shading. This is notable as the PE1A experiment was conducted in Aqueduct Mesa rather than Rainier Mesa. Interestingly, the extrapolated Aqueduct Mesa model reasonably captures the trend and variability of the BC DAS data, the solid line in blue, but it did not capture the geophone data, those blue squares. For the DAG experiment, plot C, the agreement between the extrapolated alluvium model and the DAG data is less precise, but it still is notably better than the alignment between the model and the DAG discrete sensor data. These findings indicate that emplacement geology is likely the primary factor influencing seismicity within this transitional region because of the close agreement between the data and these models. Differentiating between source types within a single emplacement geology may be challenging at this range for these data sets without a better understanding of the mechanisms that are underlying the variability. DAS observations reveal a transition in the dominant factor influencing seismicity, shifting from emplacement geology to path geology as the wave travels an order of magnitude further in scaled range. This data was collected during PE1A using the downhole fiber at the DAG site located approximately 12,000 meters per KT to the 1/3 from PE1A. To obtain this measurement, we confirmed that the DAS fiber from the DAG experiments could be reused for this study, and then observed that DAS provided a rich data set with multiple phase arrivals, rather than functioning like a single-point sensor. To identify these phases, we developed a synthetic model using the code seismic waves 4 and compared it to our DAS data. This comparison required an update to our initial geologic model of this area, incorporating a velocity gradient extending to a 4-kilometer boundary. This adjustment produced both refracted and reflected waves in the modeled zone. The presence of these waves suggests that the seismicity at this location was predominantly influenced by the path geology rather than the emplacement geology, and specifically the units characterized by the velocity gradient and that 4-kilometer boundary. This finding is significant because it highlights the impact of relatively fine-scaled geologic features on the observed seismicity in this local region. Accurately resolving these features in models and providing corrections for them for discrete sensors is critical for understanding and predicting wave behavior in similar settings. DAS enhances pattern analysis for complex wave fields near explosions. And this comparative study of data from underground chemical explosions revealed that dominant controls on the ground motion vary across yields. Between 350 and 4,000 meters per kiloton to the 1/3, emplacement geology dictated that ground motion trend for each series independent of yield, and the scatter was described by linearly extrapolating strong motion models. By 12,000 meters per kiloton to the 1/3, path geology in the upper 4 kilometers became dominant, highlighting critical geologic influences. While this is consistent with expectations, actually quantifying the distance over which these changes are happening in these smaller scale events is something that is a new result for this work. Further study is needed beyond this to compare the DAS results to the single point sensor data, and will be something that we will do in future work. Thank you.